we're asking is if the roller coaster starts from rest at the top of a hill, height h, how fast is the roller coaster going when it gets to the upside down part in the top of the loop? So we're going to do this from the point of view of work energy theorem or from energy conservation. So we can do it either way, and it doesn't matter. They both work. So let's start from work energy theorem. So we need to first start by writing down the work energy theorem. So the work energy theorem, work total equals change in kinetic energy. When we are doing work energy problems, we are talking about going from some initial position to some final position. In this case, our initial position is at the top of the hill where our initial velocity is 0, and our final position is at the top of the loop where we are trying to determine our unknown velocity. So this is our initial position and this is our final position. So we're asking what is the total work done going from initial to final. In this case, we also remind you, say that assuming that friction is negligible. So no friction. Therefore, what does work on the roller coaster car when it goes from initial to final? What does work on the roller coaster car in general? The roller coaster car, we could draw a free body diagram. It's got gravitational force. It's got the normal force. No friction, no tension, no anything else. Those are the only two forces. So the total work done on the car is the total work done by normal, total work done by gravity. So as we discussed in class, it doesn't matter what the shape of the curve is that the work energy theorem what the shape of the roller coaster is, whether the roller coaster is flat or curved, and the fact that we're going in a circle, it doesn't matter. Work energy theorem still works. Doesn't require constant acceleration. So if we take this free body diagram and we say, okay, work total equals change in kinetic energy, we can break that down to the work done by the normal force plus the work done by the gravitational force equals the change in kinetic energy. So we plug in the left-hand side, and then I plug in the right-hand side. Oh, well, let me just plug in the left-hand side. So that's just the work done according to the free body diagram. Then on the right-hand side, so that's solving the left-hand side. Then solving the right-hand side, change in kinetic energy is KEF minus KEI, just final minus initial. Kinetic energy is defined as 1/2 mv squared. So it's 1/2 mv final squared minus 1/2 mv initial squared. You see here, this is where we need to carefully define which is final and initial. In this case, the final position, again, is there at the top of the roller coaster, and the initial position there is, at the top of the loop, and the initial position is there at the top of the roller coaster. So we've carefully defined our final initial. And if we're interested in the roller coaster in different places, then we can redefine our initial and final positions. But this is what we end up getting. Sorry, well, I didn't say, because the initial velocity is 0, that's where that term went. So that's what we get. In that case, I just plugged in the initial velocity, and final velocity is what we're looking for. We're looking for the final velocity at the top of the upside down loop. So now we want to evaluate what we can evaluate. Well, I guess I just did evaluate the initial. Let's evaluate the left-hand side. On the left-hand side, the work done by the normal force is going to be the magnitude of the normal force times the displacement that the roller coaster undergoes while it's being impacted by the normal force, times the cosine of the angle between them, plus the work done by gravity. Now remember that the work done by gravity we've already figured out is mg, and we're just going to write delta y here since we already defined an h in the problem. Mg delta y, where delta y is the distance that we've moved in the downward direction. That's just a definition of work done by gravity. You could go ahead and use the definition of work in general and refigure out the work every time, but we already figured out that the work done by gravity is always going to be mg delta y, or mgh, where h is the displacement in the downward direction. Okay, so the next thing to note is to figure out what Fn, d, and theta are, and then what mg and delta y are. So the next thing to note is that Fn is actually going to vary throughout the whole roller coaster. Fn is going to vary because Fn is dependent on the various other forces on the roller coaster and the directions. So Fn can only be determined by Newton's second law. It's never equal to mg. It's only equal to mg because of Newton's second law. But anyway, Fn is unknown. D is, right, if at any point, let's just draw the roller coaster at some arbitrary position. At this position, here's the roller coaster. I'm just drawing the roller coaster. Fn is in that direction, and the displacement is in that direction. And you can draw that picture anywhere in the roller coaster, and you'll recognize that we don't know. D is the whole, is it going to end up being the whole length of the roller coaster? Fn is going to vary throughout, so we would have to integrate if we were going to actually figure out what the work was done, except for the fact that Fn is always perpendicular to D. So the angle is always 90 degrees. In this case, for something that's sliding along a surface, Fn is always perpendicular to D, so that the work done by the normal force is 0. So all we're left is the work done by gravity. The work done by the normal force is 0, and so we've got the work done by gravity. So we've got mg delta y equals 1/2 mv final squared. So that's what we get. From using the work energy theorem. Notice we haven't talked about the energy conservation, potential energies, or anything like that. This is just using the work energy theorem. We don't have to talk about potential energy. So now the question is what is delta y? I never gave you mass. Whoops. Let's give you a mass. Let's say that the mass of the roller coaster. We gave you h. I think we said h was 100 meters, and we said r, I believe we said was 25 meters. Let's give you a mass of a roller coaster. It's kind of hard to say, right? Depends on how many people are in it, but we'll just give you a roller coaster car with a mass of 500 kilograms. Let's say, it doesn't really matter, 500 kilograms. Okay, so of course you look at this equation and you say, oh well, mass cancels. You're right, so we didn't need to know the mass. It's independent of mass. That's good, right? The speed of a roller coaster better be independent of mass. That would be difficult if it was dependent on mass, because then every roller coaster would travel at a different speed, and that wouldn't be good. Okay, or every time it went through the loop, it would travel at a different speed depending on how many people were on it, and that wouldn't be good. So mg delta y. Delta y, remember, by definition, when we say that the work done by gravity is mgh or mg delta y, the distance variable, displacement variable, is the displacement in the downward direction for work done by gravity. Displacement in the downward direction. Delta y is also, you can just think of it as y final minus y initial, right? And so y final, this is y final, this is y initial. The displacement in the downward direction is what? What you got to realize is that y final is, assuming this is a circular loop, is 2r above the ground, because r is the radius of the loop. So y final minus y initial is h minus 2r. So we've got, therefore, we've got mg times h minus 2r equals 1/2 mv final squared. And now we can go ahead and solve for v final. And so what we end up getting, we solve for v final, do the algebra, plug in the numbers given, we get 31.3 meters per second. That's like 60 miles an hour. That's kind of fast. That's really fast. That would be too fast, but whatever. We took away friction. We also made the roller coaster really high. 100 meters is super high. Actually, I'm not sure that there are any roller coasters that are 100 meters high. I think there are, but only one or two. 31.3 meters per second. Okay, so that's work energy. Now this is going to be a little bit tedious, but let's do it the exact same problem again from the concept of energy conservation instead. So the conservation of energy says that the work done by non-conservative forces equals the change in mechanical energy, where the mechanical energy is defined as the potential energy plus the kinetic energy. This is the exact same equation and gives us the exact same results as work energy theorem. It's just looking at it from a different concept, using the concept of potential energy instead of the concept of work. If there is no friction, this is really important. This is a really important statement, so I'll say it again. I said it in class. If there is no friction, it means 0 equals the change in energy. Friction does no work means the change in energy is zero. It doesn't mean the energy is zero. It means the change in energy is zero. The change in mechanical energy. So this is mechanical energy. Mechanical energy. And so the change in energy is zero. That means that zero equals E final minus E initial. It means that E final equals E initial. It means that the energy doesn't change throughout the trip. The total mechanical energy is a constant throughout the trip. So what that means is that therefore PE initial plus KE initial equals PE final plus KE final. That's what we mean by the conservation of energy. In general, that's what we mean by the conservation of energy. It's context dependent, because sometimes in physics when we say if total energy is conserved, we mean all energy, but that includes any other forms of energy such as thermal energy. Conservation of mechanical energy, we should qualify it. Mechanical energy certainly means PE plus KE initial equals PE plus KE anywhere else. It's a constant. It's not zero, it's a constant. It's really important. A lot of you are going to tell me when I ask what does this statement mean, you're going to tell me that energy equals zero. I'll tell you now and say, try to store it away in your head, that it means energy is a constant, which is not zero. It just means it doesn't change. Okay, PE plus KE equals PE plus KE. So in this case, what we do is we say, at the top of the roller coaster, so I'm going to go back up to the picture of the roller coaster and say, well, total mechanical energy here, E initial, equals PE initial plus KE initial. So we have to ask, what is the total mechanical energy? Well, it's starting from a height h above the ground. So the first thing, in order to define the potential energy at a point, remember we have to define our zero somewhere. So I'm going to define the potential energy equal to zero at the ground. So then the potential energy at the top of the roller coaster, at the top of the hill, is just going to be mgh. That's potential energy, mgh, where h is measured upwards. Potential energy due to gravity, potential energy due to gravity, where h is measured upwards. That gravity is the only potential energy we've got so far. We will add in potential energy due to springs later. Okay, so potential energy due to gravity is mgh, and potential energy due to kinetic energy is 1/2 mv initial squared, and v initial is 0. So the total mechanical energy at the start is just mgh. Then the total mechanical energy at the final position, right? The total mechanical energy at the final position, E final, equals mgh final plus 1/2 mv final squared. And h final is equal to 2r. Right, where h final is equal to 2r. So that's the final potential energy. I keep saying the wrong word. The final potential energy. So E final is potential energy final plus kinetic energy final, which is mgh final plus 1/2 mv final squared. And the fact that energy is conserved, we can just write I'll just go ahead and write without the zeros. Mgh initial plus 1/2 mv initial squared equals mgh final plus 1/2 mv final squared, and then plug in what we know. H initial is just what we had determined as h in this problem, 1/2 mgh plus 0. H final is 2r, and v final is what we're trying to solve for. So that's energy conservation. We've conserved energy. We wrote the total mechanical energy at the start equals the total mechanical energy at the end. And we solve for V final. And what we get is the exact same thing as before. Square root of 2g h minus 2r equals 33.1 meters per second. 31.3 meters per second. So what you need to realize here is simply that we can solve this problem from a work total equals change in kinetic energy point of view. That's the work energy theorem. Or we can solve it from a conservation of energy point of view. PE initial plus KE initial equals PE final plus KE final, if there are no non-conservative forces. And we'll do a problem where there are non-conservative forces sometime soon, but for now, conservation of energy. And both ways really give us the exact same thing because they're really both the same equation, just written with a different concept in mind. Which side of a turkey has the most feathers? The outside. Ha ha ha.